This is my mini homemade 3-axis CNC mill. Let me show you how I designed and built it. Here's a rough BOM for this build. My budget was $500. This is the power supply. It takes power input from the wall AC here and it splits it off to two places. In parallel with each other, it goes to the DC motor controller and the DC-DC converter. The motor controller is what powers the spindle motor. It's speed adjustable and reversible, and the DC-DC converter steps the voltage down to power the CNC shield and then the 4 stepper motors. The power supply is a 24 volt supply. The motors run off 12 volts. So this converter is a 24 volt to 12 volt converter. My motor controller here, there's 3 things plugged into it. This is just a digital display that shows the PWM duty cycle from 0 to 100%. This is a potentiometer that varies that. And this is the forward, reverse, off control switch here. I've also got these 2 shunts connected. One of them is in the DC motors power, and the other one is in the CNC shield stepper motor power after the converter. So I should be reading around 12 volts here and around 24 volts here. The power supply itself also has an output display that shows its voltage, and that voltage is adjustable with this potentiometer. The second shunt is not on right now at all. That's because the circuit is being broken by the motor controller. But if I set it on to one side and then turn the potentiometer past 0, duty cycle of 11%, the motor starts spinning, and you can see on the shunt 2.87 volts. That's the average because it's a low duty cycle. But if I turn it up, that'll increase. And at 100%, I'm getting 18 volts there. The CNC shield voltage is keeping up at 12. Motor spinning quickly. These shunt meters I'm using don't read an accurate amperage at low current levels. There is a potentiometer on the back. You can adjust to calibrate that, but they just don't work below a couple of amps. Here's my CAD model of the entire assembly. I pretty much entirely finished this model before I started assembling anything at all in the real world. A few general design philosophy things. Every single lead screw paired with linear guide rods, the screw is exactly in the center and on the same plane between those guide rods. That prevents there from being net moment around any of the subframes, which may cause reaction forces and friction and binding up on these rods. Same thing for the X lead screw. It's exactly between its 2 X guide rods, and that philosophy worked out pretty well. I never ran into any issues with anything binding up or having friction. And for the Z axis, I'm using 2 lead screws and 2 motors. Their 2 guide rods are also exactly in the same plane, which is the exact same plane as the spindle. The footprint of the device is about 500 millimeters by 500 millimeters, and it's also about 500 millimeters tall. Everything you see in green is 3D printed parts. I did not really include the limit switches in this model. I played around with their positions a little bit, but those I really just placed after I built the entire thing. I didn't put a ton of unnecessary time into modeling every last detail of every off-the-shelf part true to life, which wasn't an issue except for one mistake that I made in this design. Was with the vise, I did not model the handle, which would stick out this way, and the movable jaw.
and I did have a pretty significant interference issue with that. Thankfully, I was able to make that work with the different vise, but that could have really been a much bigger issue. I didn't really model hardly any of the nuts and bolts, mainly just because that would have taken a lot more time and it would have made the assembly a lot more complex, and I didn't really need to. That did cause me to run into a couple of little clearance issues, but those were all pretty easy to solve, mainly just by getting different bolts and hardware. In the real world, I actually flipped the whole Z-axis subframe around 180 degrees, so the extrusions are on the opposite side of the motor. It actually doesn't matter which way that goes, because either way, the spindle, motor, lead screws, and guide rods are all exactly in the same plane. I mainly made that change because it made the wiring a lot more convenient, especially when it's moving up and down. I didn't want to risk anything getting caught and tangled, and I had a couple of minor little interference issues with the ends of a few bolts between here. I toyed with the idea of adding a second bearing for the lead screws mounted to the frame here. I didn't end up doing that. I just stuck with one on the top. These do not allow the lead screw vertical movement at all. So the forces on the lead screw are transferred into the frame, and just the one up there was sufficient to prevent there being too much of an axial load on the motor itself. I wanted to keep as much of the weight and force going through the frame as possible. I've just started assembling the frame. I'm using this 2020 aluminum extrusions because it's easy to mount stuff to and bolt together. It's relatively cheap and sturdy, and it has these T-slots in the corners. Here's what the cross-sectional profile of it looks like, if that'll focus. So I'm using these T-slots to mount a lot of stuff to it, including these corner braces in the corners. But the main structural element of the corners is these M6 bolts that I'm running all the way through and into the next section. I tapped with a tap that central hole for the M6 bolt to mount the corners together, and then reinforce with these braces. Here's where I'm at so far. Just got the base all put together. I'm making these adjustable feet by threading a bolt into a tapped hole and then using a jam nut to lock it at a certain height. At this point, I've got all 4 feet installed and the 2 vertical main supports. I'm mounting my guide rail supports in the T channels here, and there's a little bit of play both side to side and angle, and that's going to allow me to clock it in just right and then tighten it down to where the 2 guide rails are exactly parallel with each other. I've got the X-axis completed here and assembled. It's running fairly smoothly. I'm running into an issue with these bolts on the side mounting the rail blocks onto the subframe here. The heads just keep snapping off the bolts. I figured out what was going wrong with my bolts here. I was actually bottoming them out within these holes, which are not threaded all the way through, continuing to try to tighten them down and just snapping all the heads off, trying to snug them against the backing plate. Simple solution is I've tapped the holes so the bolt can run all the way through. That prevents the bolt length from being critical in what's effectively a blind hole. This is the end that'll be driven by the stepper motor. The lead screw, I've got it running right through the subframe there on the X-axis gantry to save a little bit of vertical height so I don't have to go over or under it. And then that brass nut on the other side of the subframe is what gets driven by the lead screw and pushes the entire assembly forward and backward. I think that'll actually be one of the weak points in the system, because when it's pulling like so, it's only 2 little M3 bolts that are in tension holding the full force against the thrust of the tool into the work. These through holes in the frame extrusions are not going to significantly reduce their structural integrity. That's because the cross section of this material, it works kind of like an I-beam under a bending stress. When the weight of the vise in the part is bending it in this direction, the majority of the stresses
are going to be in the very top flats and the very bottom flats. And when the tool is thrusting into the work and there's a bending stress in this direction, the majority of the stresses will be in the side flat parts. But under bending from either direction, there will be relatively little stress in the center where I've taken material out from.
I'm using these NEMA 17 stepper motors for this build. I've got them mounted to the frame with these 3D printed PLA brackets, and this one's actually going to share two motors. It'll have one of the Z-axis motors also. There's just a coupler connecting them to the lead screw. I've got the X-axis all tested and adjusted and tweaked to where everything's nice and parallel. It's running smoothly and there's as little resistance on the lead screw as I can get. This is the assembled Y-axis gantry. It's built in much the same way as the X-axis gantry. The vise will be mounted like so, using these through holes that have some room to align it and get the best parallelism for machining. Also keep in mind the lead screw is not bearing the entire weight of the vise in the work. That'll be the guide rods, which are 4 points mounted on these 4 corners. I ran into a slight clearance issue with these socket-headed cap screws on my linear guide rod, so I'm swapping them out for some lower clearance hex-headed bolts. Again, I'm adjusting the placement of the guide rods to make sure everything's running nice and smoothly and parallel. I got a little creative with this bracket right here. It mounts both this pillow block and the stepper motor, and it has that linear guide rail going right through it. The reason that I'm waiting until last to do the triangulation members, which will go somewhere in this vicinity, is so that I still have a little wiggle room to adjust these main vertical supports. It's really important that everything is square and parallel, and this way I have a little bit of adjustability and wiggle room before I set everything in its final place. I'm having a little bit of difficulty getting these horizontal members exactly perpendicular to the vertical ones and parallel with the lower ones, mainly because I cut both faces of this by hand with a hacksaw and they're just not perfect flat faces. But these 90-degree angle brackets help a lot, and I still have the ability to loosen these bolts and make minor adjustments to the joints to account for any imperfections. I'm happy with how things are moving and running so far, although it's a little bit noisier than I expected. I suspect that's because of insufficient clearance between the lead screw and the aluminum extrusions close to where the lead screw nut is. There's not a whole lot of clearance there, and the lead screw may be hitting the inside of that. Additionally, right now I'm not micro-stepping the motors at all. I'm just full stepping them. And if I do start micro-stepping them, they'll likely run a little smoother and potentially quieter. I've just finished assembling the Z-axis gantry. It'll be mounted in this area, translating up and down. The main spindle will be mounted to it about here, so will the motor. The most significant force this part will experience is going to be a plus Z-axis force right in the center, which will be when the spindle with a bit plunges into the part, and it'll kind of apply an upward force here that wants to bend the part upwards like so. And with these two bars that make up the subassembly spaced out, it gives me more material away from the central bending axis of the part, which will make it deflect less with any given amount of force. Of course, there will be an equal and opposite force in the minus Z direction, and by nature of this geometry, that'll always be split evenly between this guide rod and that back one. These bars are made of a much harder alloy than the 2020 aluminum extrusions are, but if deflection becomes a problem in this direction, there's a couple things I could do. I could space the two mounts further apart to give it a better advantage geometrically that would reduce the amount of deflection, or I could add more linear guide rails
along this axis, say one here for a total of 4. That would reduce the amount of force on each individual one by half. Here's what the main vertical Z-axis supports look like. Here's the Z gantry all mounted up. The reason I have the nut mounted facing up like this is so that when the threaded rod is pushing it down under a lot of reaction forces when the tool is plunging into the part, the forces between the nut and the frame here are pushing them together. That way the threaded connection between these bolts and the metal here is in compression rather than tension. So the threaded rod will be supported by a bearing towards the top and also by the motor down here at the bottom. I may add another bearing here, but again, I don't want to over constrain it too much and make it too difficult to get everything aligned straight. This will be the first test of the Z gantry. Now I've got all 4 motors connected to the microcontroller, so let's see everything moving together all at once. Underneath each of the stepper motor drivers here are 3 pairs of extra pins, and with those you can add jumpers to specific ones to change from full stepping, half stepping, quarter stepping, eighth, and 16th, which I'll be trying out here in a second, and so I'll be putting a jumper across all 3 pairs of those pins. There's all 3 jumpers in place. And this is all 4 motors running simultaneously on 1/16th micro stepping. Hopefully you can tell, but it's a lot quieter now because the torque is being applied so much more smoothly. I've just bolted on the spindle and the vise. Both have a little bit of adjustability due to the holes being extra wide for the bolts, so I can adjust the angle of the tool relative to the vise, and I can adjust the angle of the vise relative to the tool. Stopped short because of a little clearance issue between the vise handle and the frame in about the last inch or 2 of travel in this direction. This is a different vise with a slightly different bolt pattern that lets me mount it 90 degrees from how it was before without changing anything else. And now I've got plenty of clearance. Here's kind of an interesting view of the undercarriage, so to speak, after I've just mounted the new vise. I've added some more members to the frame here to make it a little more rigid. These triangulations and these 2 cross members in the middle. This one I put up as high as I could get it, and this one I chose that height so that when the tool is all the way up as it is right now, it still has clearance below the bottom of that. That means it won't get in the way if I'm using a really short tool with a really tall workpiece. For these diagonal braces, each of the bolts is connected to the frame rail behind it with one of these T-slot nuts, and that lets me adjust it up and down, also left and right down there, to fine-tune the nod of the tool and keep everything adjusted parallel and straight. Here it is more or less going through the entire travel. Now I'm going to power up the spindle while the rest are running and see if they run happily all at the same time. Now I'm mounting the motor for the first time. I can adjust it left and right on these frame rails to set the belt tension, and I can also adjust the angle a little bit to get the belt nice and straight. I've got all the main electronics mounted onto the back. The DC-DC converter and the motor controller are both just bolted onto the frame with their existing mounting holes. The Arduino and shield and the main power supply are bolted on with some pretty simple 3D printed mounts. I've mounted everything with motor clearance in mind. As it moves up and down,
Nothing extends out further than the front face of these frame rails. I've got that display visible.
Here's what the wiring looks like from the back. I've got the output of the 24 volt power supply going into the input of the DC-DC converter, and then that's 12 volt output going straight to the Arduino and CNC shield. The outputs from all the stepper motor drivers, I have them following the channels and the aluminum extrusions to their respective stepper motors. These are the inputs to the DC motor driver, and this is the display for the DC motor driver. And the USB going to the PC, I've just left it dangling off to the side. Here's what it looks like from the front. I have my 24 volt output going to both the DC motor controller and the DC-DC converter. This is temporary, just to mount these controls here, nothing fancy going on, a little 3D printed mount. Same with this display. And I've left enough slack in the wires here so that the motor still can go through its entire travel without being limited by the wires. I had to splice in some more wires to the connector for the Y-axis stepper motor because it wasn't long enough to reach the Arduino, and I've left enough slack here for the gantry to go through its full travel. Made a mistake before, but just fixed it. I had the neutral wire connected to the ground connection, and it should be connected to the neutral. These come down the side of the frame to the wall source. I've left a little slack in there to add an emergency stop button at some point that will cut all source power to the power supply. All that's really left is to add some limit switches on the X, Y, and Z so that it can automatically zero itself. But for now, I'm ready to do some test cuts just by manually jogging it around. This is the first time I'm running the spindle off of the motor, and this is at pretty low RPM, 4% duty cycle. Let's go up to 100% gradually. Here's a few final checks of the movement system before I start doing some cuts. By the way, I'm temporarily using this as my emergency stop button. This program, CNCjs, is what I'm using to control the machine so far. I've just been manually feeding it G-code in the console, but I'll be able to jog it around with this and feed it actual G-code from a CAM program. The important thing at the moment is that I've set the travel resolution to 400 steps per millimeter. This is how I calculated the step resolution, 1.8 degrees per step. That's a property of the stepper motors I'm using. This factor 16 comes from the 16x microstepping on the controllers. 8 millimeters per revolution is the pitch of the lead screws that I'm using, and so that gives me 400 steps per millimeter. The initial position of my x-axis is almost exactly 13 millimeters here. I'm going to give it G-code to move 120 millimeters in the plus direction, and then I'll measure it again, and it should say 133 millimeters. So we're at 0, 0, 0 on the computer's coordinate system. I'm going to have it move 120 millimeters in the plus X. So over in the console, I'll type G0 X 120. And actually that's the X, but we'll notice the dot starts to move as it tracks the position of the machine. And you'll notice it says my X position is positive 120 millimeters up here. So let me go measure the machine and see what the actual difference was. I just realized I measured the Y pre-position, but then I moved the X. So now I want to move back to X0, Y120. So let me make sure we're in absolute coordinates with G90. Then I'll go G0,
X0, Y 120. So now it's moving in the X and Y direction simultaneously, and it should reach 0, 120, and then I'll measure it. That'll also give me an idea if the X is out of whack. And here we are, 120 millimeters from where we started. Perfect. I've got a 1/4 inch 4-fluted end mill mounted in the spindle, and a random old piece of relatively soft wood I had laying around. I'm just going to turn on the spindle and manually jog it through the wood and see what happens. This will be the first ever cut on this machine. Pretty decent looking cut here. No sign of any walking away or wandering. Pretty smooth edges. Here towards the end, I plunged 2 millimeters deeper into it and then took the rest of the cut out. Looks like the walls of the wood got a little choppy there, but overall, I'm very satisfied with that for a first cut. So there's a few things I had to change within the config to get the limit switches working. First of all, this line in the config file, I commented that out because it turns out by default the pin on the Arduino used for the Z limit switch actually is outputting a variable voltage to control a spindle RPM. I disabled that so that I could use it for the Z limit switch, and I'm controlling the spindle speed manually anyway. Also over here in the main console accessible through CNCjs, I've changed this variable 23 to 3 based on this table to invert the direction of the X and Y homing, but not the Z. That's just based off the physical locations I have my limit switches on the actual machine. Also within the config file, I've uncommented this line to allow me to home axes separately, and that was just so that I could test them individually. And I'm leaving the actual homing cycles as the default right now. In the future, I'll change this to use 2 limit switches on the Z-axis, but for now I'm just using the default homing cycles. This is the homing cycle in action. First, it's going to home the Z switch right here. Next, it's going to simultaneously home the X and the Y. And there we go. Now we're at our 000 home position. I definitely need to make this one a little stiffer and stronger to get good repeatability out of that. I was having a strange issue with basically false triggering of this limit switch, and I believe it was actually due to noise in the switch cables due to induction from interference in the other motor cables that it's bundled along with. And this is the longest cable. So I fixed that by rewiring it a little bit to where the switch wires are always on the opposite side from the motor wires. Another thing that helped a little bit with that false triggering issue was enabling this setting, software debounce, and that basically tries to compensate for the pins of the limit switches wanting to float a little bit due to the interference from the other cables. Now it's time for my first ever cuts of actual metal on this machine. This is a piece of 6061 T6 aluminum and a 1/4 inch 4-fluted carbide end mill. Not horrible, but there was quite a bit of chattering and movement, so I'm going to try a little bit of a shallower depth of cut. Alright, for this next pass, I'm going to do the same depth and speed, but I'm going to overlap the previous pass by about half. Still sounded like there was quite a bit of chattering on that cut. Yeah, that looks kind of terrible.
Let's try a new climb milling pass and see if it gets any better. That looks pretty good. Pretty smooth edge. Nice smooth face as well. So definitely climb milling is working a lot better on this machine. Next I'm going to try some real shallow facing cuts on the side. Also, I'll definitely still be doing climb milling. Got a little chattery over here because for the first couple of passes I was doing a depth of cut that I think was a little too high. But over here it looks pretty good. Now I'm going to do a few climb milling facing passes across this face using about the entire length of the end mill that I can. Alright, this little section is looking pretty good. You can ignore everything that was happening over here, but I figured it out on this one. That's very smooth to the touch. Here's the preview for the G-code I'm about to run. I generated it with SolidWorks CAM. I'm going to zero out my work offsets after I just manually jogged the tool over to that 0, the corner that I'm using as a 0. Here are the results of that last few passes. I had to stop it a little early because I ran out of time, but overall not too bad. The edges came out okay. You can see it kind of stopped here and here, and that's because this corner was a little lower and this corner was a little high. So I'll have to work on leveling out the vise with the travel of the machine. This is a little bit of overlap from a different cut, but you can see there's still a little bit of chattering going on up on the higher edge there. You can ignore this. This is a quick little engraving toolpath I put together to leave you with. Here's a simulation. So I'll show the real version of that in a second, and that'll be the end of this video. I'd like to thank you for watching, and stay tuned for part 2, where I'll get more into the full performance of this whole thing, and some upgrades, and making some more awesome parts. So thanks for watching. Not bad.